Okay, we're going to continue with chapter 2. And remember, chapter 2 has to do with the chemistry. Now, the formation and the function of molecules depend on bonding between atoms. Atoms with incomplete valence shells are going to share or transfer electrons that are on the valence shell with other atoms. Those that have complete valence shells are not going to do this. Remember, they are happy, they are inert, so they are not reactive. And what that means is they're not going to create bonds with another atom. These interactions result in atoms staying kind of close together, so they might be held together by strong attractions or weak attractions, and these are called chemical bonds. A molecule is the term used for the connection or the result from the connection of two or more atoms being held together by these bonds. Covalent bonds are the strongest. Covalent bonds are the sharing of a pair of electrons by two atoms, and the atom could be the same or it could be a different one. Now, in a covalent bond, when the electrons are shared, they count as electrons that are in each of their valence shell. If we look at the hydrogen atom, the hydrogen atom, as you can see, we've got the electron cloud. Remember, hydrogen only has one electron. Okay, so remember, this is the first shell. So it fills with two electrons, so each of them need one more electron in order to fill that valence shell. Now look, as they come closer together, now we've got the electrons kind of pairing up, right? So they're going to form a covalent bond. Once they are together, now we have a covalent bond. They are paired. So this means that they are sharing these electrons. So this hydrogen has two electrons in its outermost shell, the valence shell, and this hydrogen also does. So they're sharing it, and each of these electrons count as electrons in that valence shell. Now, covalent bonds can be single bonds, as I showed with the hydrogen, right? And when we look at molecules and the way they're described in the textbook, you will see that they are described in a number of different ways. So here we could talk about a molecule of hydrogen by its name or its molecular formula. So the molecular formula tells you what atoms and how many of each are in the structure. The electron distribution diagram shows the electron distribution. So you've drawn the electron distribution, hopefully you practiced, but you can see the electron distribution diagram of this whole molecule where it shows the sharing of these electrons. You could also draw it like this. So this is called the Lewis dot structure. The Lewis dot structure shows the sharing of these electrons. However, it's not like the electron distribution diagram, where the electron distribution diagram is going to show all of the electrons in each of the atoms. The Lewis dot structure only shows the electrons that are in the outermost shell or the valence shell. You could draw the structural formula, which basically shows a line which indicates that there is a covalent bond there. So a solid continuous line means that there's a covalent bond. There are other types of lines, which I'm going to talk about later. So this shows that these two hydrogens are sharing their electrons, creating a covalent bond. And this shows the space filling model. Now, this shows a single will be double bonds, or they could be bonded in other ways. So here, this shows the structure of water, which will be the subject of the next chapter. However, water has two atoms. You can see how many of each one, but it doesn't show the structure. You can do that with the electron distribution diagram and also the Lewis dot structure and the structural formula. So you can see that there are unbonded pairs of electron and those pairs that are shared and bonded to different atoms. And then, of course, this shows the space filling model. Again, these are single bonds. And this shows additional single bonds right here. So we have methane. Methane, here we've got the name, the molecular formula, and the electron distribution diagram showing all of the electrons in each of the atoms and also showing the sharing of electrons. And then here you can see the Lewis dot structure only shows those that are being shared in this case, but those that are in the valence shell of each of the atoms. And the structural formula indicates that there are 4 covalent bonds. Each of these hydrogen are covalently bonded to this carbon. And here is the space filling model. Now, you could have a double bond, right? So here we have oxygen. Oxygen can double bond with another oxygen, but it can also double bond with other things as well, like carbon. But in a double bond, there's 2 pairs of electrons being shared. And the same rules apply. Each of these 4 electrons count as electrons in each of the atom's valence shell. And again, you can see the Lewis dot structure showing just the valence electrons. And when you show double bond in the structural formula, it's going to be 2 solid lines. And then here is the space filling model. Bond. Not many atoms form triple bonds. Nitrogen is one of them, one of the only ones, if not the only one. So again, this is sharing of 3 pairs of electrons. Nitrogen can triple bond with itself, and this shows 2 of the Lewis dot structures, and then this is like a hybrid between the Lewis dot and the structural formula. And here you can see the electron distribution diagrams and the space filling model. Now, we talked about this before with the valence shell. So the term valence and valence shell, the valence shell refers to the valence shell, right, where the electrons are. But valence is basically the number of electrons that it needs in order to fill that valence shell. For instance, hydrogen needs 1 electron to fill the outermost shell or the valence shell, so its valence is 1. Carbon needs 4, so its valence is 4. Now, covalent bonds can form between atoms that of the same element or atoms of different elements. Covalent bonds between the same elements are ultimately called molecules or molecular, like this is molecular oxygen, this is molecular hydrogen. A compound is a combination of 2 or more different elements, right? So you can see the water is a compound and C6H12O6 is glucose. That is also a compound. Now moving on, atoms in a molecule can attract electrons in varying degrees. Okay, so this is referred to as electronegativity. So each atom has a specific electronegativity, and there's a relative number associated with it. So those atoms that are more electronegative, they're more attracted to electrons. So they're going to pull electrons more towards itself. Non-polar covalent bonds, okay, so remember, covalent bonds are sharing of electrons. Those that are nonpolar mean that the atoms have, their electronegativity is about equal. So they share the electrons equally. Polar covalent bonds, on the other hand, one atom is more electronegative than the other, so that one atom kind of pulls those electrons. It likes to hog the electrons, so the electrons are going to be closer to that atom than they are going to be the other atom with the lower electronegativity. So let's talk about water. Water is one of those kind of important molecules for life, but it's important mainly because of its properties, right? So it's got these special properties. It's got that bent configuration because of the unbonded electrons, and also it has polar bonds within it. So since we're talking about polar bonds, remember polar bonds occur due to the unequal distribution of electrons within the covalent bonds, right? So water, we have oxygen and 2 hydrogens. Oxygen is extremely electronegative. It's actually one of the most electronegative atoms that there are. Hydrogen is not very electronegative. So when hydrogen bonds to oxygen, the electrons that are shared are going to hang out closer to the oxygen. So the oxygen kind of pulls those electrons towards itself. So it likes to kind of hold on to those electrons, creating this partial negative charge on the oxygen side and partial positive charges on the hydrogen sides of water. This is polarity, right? So polarity really ionic bonds, right? So atoms sometimes steal electrons from a partner, right? So it's going to become a bonding partner when it steals electrons because it's just going to basically take that and then they're going to be attracted to one another. An example is the transfer of electrons between sodium and chlorine to create sodium chloride. Remember that example that we saw earlier. So after that transfer, right, let's say sodium is going to lose an electron, it becomes positively charged. Remember, I kind of mentioned that, right? So it's a full positive charge on that sodium. And then since chlorine is going to gain an electron, it becomes negatively charged. These are called ions. So ions are elements or atoms with a full charge on them. So there can be a cation, which is positively charged, or an anion, which is negatively charged. Now, if we look at sodium, remember sodium? Okay, so sodium has that one electron in its outermost shell. Now, in order to fill that electron, that outermost shell, it would need 7 more. It's more likely that it's going to lose that electron than it is going to gain 7, right? Energetically, it doesn't make sense to get 7 electrons where you could just lose one and be happy. So chlorine conveniently needs one, right? So chlorine is in group number 7 in the periodic table. So it has 7 electrons in its outermost shell, so it needs one more in order to fill that valence shell. So it steals that electron from sodium. Now sodium and chlorine are both happy. Both of them. The valence shell is now filled. But now they are charged. Okay, so now sodium becomes positively charged because it's lost an electron, so it has one more proton than it has electrons. Chlorine becomes negatively charged because it's gained an electron, so it has one more electron than it has protons. This creates salts, right? So when two charged, oppositely charged atoms come together, they typically create salts. And one example would be this sodium chloride. Now, hydrogen bonds are another form of interaction. Hydrogen bonds occur between molecules, not within molecules. So here we have a water molecule. Remember, these are polar covalent bonds right here. And here, ammonia, these are polar covalent bonds because now nitrogen, in this case, has a higher electronegativity than the hydrogens. So this creates a partial negative charge on this side. Now, hydrogen bonds are going to occur between hydrogen, of course, that's why they're called hydrogen bonds. Hydrogen of one molecule, right here in this case, water, and basically like an attraction between partial charges with another molecule. In this case, the nitrogen, because it has a partial negative charge due to that polar covalent bonds that are formed with hydrogen. Okay, so that is a hydrogen bond. Hydrogen bonds are denoted by dotted or dashed lines. They're not straight lines. So you can see straight continuous lines. These are covalent bonds. Dotted or dashed lines mean that there's a hydrogen bond that is happening there. Now again, remember, it's important that you know that hydrogen bonds form between molecules, not within. Now, van der Waals interactions, this is a basically momentary dipole moment, right? So it's just when the electrons are not really evenly distributed, they might accumulate just randomly on one side of the molecule. which would attract that molecule to another one where the electrons are distributed unevenly to another side randomly. Okay, so this creates an attraction, and this attraction is called van der Waals interactions. Van der Waals interactions are also sometimes called London dispersion interactions or London dispersion bonds. These occur basically between all types of molecules. Now, collectively, all of these interactions, some of them may be strong, some of them may be weak. But even just the weak ones, if there's many, many weak ones, it creates a strong bond. And this kind of occurs in the gecko's toes. So here in the gecko's toes and the hairs, the tips of them are flattened, right? So it increases the surface area. And those hairs on that larger surface area get to interact with the wall, the surface of the wall, and it allows them to walk on the ceiling and on the wall without falling. Now we're going to talk about the structure-function relationship within molecules. So we kind of touched on that a little bit with within organisms, right? So remember that hummingbird with the long beak, and I remember I mentioned the wings span behind its body so that it can get close and inside those flowers to be able to. Now, the shape of a molecule at the molecular level is important for its function, especially the size of that molecule as well. Now, the molecule's shape is determined by the types of atoms and the position of those atoms and the orbitals where the electrons belong. Right? So in a covalent bond, it's not important to memorize this or anything, but the s&p orbitals might hybridize to create specific molecular shapes, like a tetrahedral shape. Okay, this happens in methane, as we saw the space-filling model previously. Look at other shapes that can form. Now, water is a little bit different. It only bonds to 2 hydrogens, so then there are 2 pairs of electrons that are unbonded, but they're still paired. Right. Those unpaired or unbonded electrons take up a lot more space. So it creates this bent structure that's really important for water's function. So you can see this is where the unbonded electrons would be. So it creates almost a you could see as a tetrahedral shape, even though there's not as many bonds as would be in methane. So you can see there are 4 bonds in methane, same type of shape. Now, this is important with pharmaceuticals, right? So the shape determines how the molecule would work. Some molecules recognize proteins that are inside the cell. So an example would be a receptor for for an endorphin. Endorphin is basically a molecule that well, there's natural endorphins that our bodies make in response to an injury to help relieve pain. Well, pharmaceuticals are made in the lab to mimic those. So it's important to know the business end of the natural endorphins so that we can actually create a molecule that looks like it, right? So it has the same shape and same size so that it can bind to the same receptor and work the same. Really concludes this section, chemical bonding and the importance of molecular size and shape with its function. I talked about molecules and compounds and the difference between them and how molecules are formed by all of these types of bonds: covalent bonds, ionic bonds, hydrogen bonds, and van der Waals forces. Also the structure-function relationship within molecules. All right, thank you for listening.